So we've been taking forever on chapter 2, it seems, just talking about how atoms are organized, where the individual particles are, protons, neutrons, electrons. And again, I keep returning to the point where electrons are really the fundamental part of chemistry. It's because it's the sharing, the taking, the giving of electrons. It's pretty much all of chemistry. So we had talked about, where we left off is talking about differences between ionic compounds, where electrons are transferred from one atom to another and we form ions, and covalent compounds or molecular compounds, where electrons are shared between atoms. And one of the things that's unique about ionic compounds is that they're almost always solids, because they form this sort of lattice of charged particles, positive and negative particles, all sort of packed together in this regular form, which is where you almost always see crystals of ionic compounds, like table salt, any kind of salt, because they're all salts really, form these sort of solids. And it takes a lot of energy to melt them, and even more energy to boil them, obviously. And the thing about ionic compounds, they don't conduct electricity when they're solid. So you can take a couple of probes to a battery and put them up to a hunk of salt, and you're not going to complete a circuit. But when you melt them, and you can see down here these three different setups. Basically, what's happening there is you've got some sodium chloride in a dish with a couple of probes in it to a battery that's connected to a light bulb. And when it's cold, when they're solid, you don't see any conduction. And then when you start heating it, oh, excuse me, bad air today. When you start heating it, you can see with the last picture, the light comes on, the electrical circuit's completed. Anyone tell me why solid ionic compound does not conduct electricity, but a liquid ionic compound does? What's the difference there?
May I say this one?
Go ahead.
Because the ions are packed very closely when they're solid. When they're liquid, then the ions can move relatively freely, so that the electrons can also move relatively freely.
Yeah, it's the movement. It's the same reason why if we took that same salt and put it in water, that would be able to conduct the charge as well. It's because they can move. You're absolutely right. When it's a solid, those charges are in place. They can't go anywhere. They are stuck in a particular, like a lattice-like crystal environment. They're not moving. When they melt, then they can freely move around. Or if they're dissolved in water, they can also freely move around. And as we know, or hopefully we know, electricity is the movement of charge. And so if the charge can't move, we can't conduct electricity. And you can see here that we have to get up to a temperature of 800 degrees in order to melt table salt. And in order to boil it, we need to get to a few thousand degrees. So this is also something we've been dealing with already. But an ionic compound, just like a molecular compound, is neutral. It doesn't have a net charge. There's charges in it, but those charges have to balance out. And so the number of positive charges have to equal the number of negative charges. They have to equal 0. And so when we figure what particular ions are going into an ionic compound, we have to figure out how many. And when we're figuring out how many, it's like, what's the smallest number of positive and negative ions we can put together that equals 0? So in this particular instance, we have aluminum. And hopefully by now we know that aluminum is always +3. It's in group 13, it's always +3. And oxygen in group 16 or group 6 needs 2 electrons to get the chemical nirvana. So it's always -2, always, always, always. So if I have a +3 and a -2, I'm going to need 3 of these and 2 of these to get to 6 charges. And that's the smallest number that's in common between 2 and 3. So that's the smallest number of whole number of ions that will then balance out. So then Al2O3. What's the name of this compound? What will we call it? Nicholas.
Is it aluminum oxide?
What about aluminum 3 oxide? Wouldn't we call it that?
Okay. Aluminum 3 oxide.
No, it isn't aluminum 3 oxide.
Oh, okay.
It's not aluminum 3 oxide because it's always +3. And so we can assume that it's +3. It's +3 all the time. We only use the 2, 3, 4, 5, whatever in brackets if it's a transition metal that has different or what we call different valences or different charges. Aluminum is always +3. Calcium is always +2. So we don't have to say that. Don't give up too soon. You had the right answer. I say that to students all the time. You're usually right the first time. The minute I poke you with a stick, you give up. I mean, no. I'm just being the devil's advocate. So let's talk about transition metal cations. Good transition. Captain Segue here. So these elements, we know, these are the ones in the middle between, we have group 1 and group 2 on the left side, and then 3, 4, 5, 6, 7, 8 on the right. And in the middle, we have these weird elements. They're all metals, and we're going to get to this today when we talk about how the electrons are organized. Their electrons are organized in such a way that they're not always the same charge. Like for instance, iron basically has 2 different valences or charges. And it depends on the conditions in which it's forming an ionic compound. So if we have FeCl2, that means we can deduce what the charge is on the iron, because chlorine is always -1. It's one of the halogens. Remember, it's in group 7. And so it needs 1 more electron to get to the happy place. So it is always -1. Fluorine is always -1. Iodine is always -1. And so basically, when you have a compound like that, FeCl2, you can figure out what the charge is on the iron, because you know what the negative charge is, and then it's got a balance, right? So chlorine, 2 of them, chloride ions. If you have 2, that's -2, got to be +2. And so we would say iron brackets 2 chloride. Same thing if there's 3 chlorines, they're all -1, all -1 as chloride ions. And so it's got to be +3 in that particular example. So we basically use what I like to call the crisscross applesauce rule. That's sort of like the simplest way to figure out how many ions of each kind are going to give you a balanced charge. And that applies to monoatomic ions like chloride, fluoride, bromide, calcium ion, sodium ion, whatever. And if we have polyatomic ions, and I want to point out, remember in my, I sent out an announcement yesterday that I included basically a reference sheet. This is the sheet that I would give out during an in-person exam. And so these are the sort of things that I don't want you to have to memorize. But this is the sort of information you would have. And one of the things, it's in the first module of Canvas, and it's also in that particular announcement. It's as a PDF attachment. One of the things it has is a list of all the polyatomic ions. You don't have to memorize them. Sulfate, sulfite, all that kind of stuff. So go to that, print that out, just have it with you when you're, taking tests or doing, just working on problems. Because yeah, I just want you to know the rules of how to use it. I don't really care that you memorize the difference between bromite and bromate. Okay, the important thing is that they're different ions. Okay, but when you have a polyatomic ion, you need to bracket the whole thing. One thing I have noticed students doing, which is a problem, is, let me annotate a little bit here. When they are writing something like phosphate. So phosphate ion is PO4, and it has a -3 charge. So if I need 2 phosphates, let's say because I've got vanadium plus, let's say vanadium plus 2. And so I need more than 1 phosphate to sort of balance that out. So what I would do is I need 2 phosphates and I need 3 vanadiums. I'm going to crisscross them. So I would write V3 brackets PO4 2. Now what I'm seeing some students do is instead of going PO4 2, they will write that as P2O8. That is not correct because PO4, or the phosphate ion, is a singular thing. Those atoms are connected in a way that we'll get to in a later chapter. Those atoms are connected in a very specific way. P2O8 is a completely different thing. That is a completely different ion. That is not two phosphates. I don't know what you would call that. It's something else altogether. So don't do that. Make sure that when you have a polyatomic ion, you show that it's I have more than 1 polyatomic ion. You don't write it like that because that is no longer the polyatomic ion we're dealing with. Okay. Okay. Let us continue. So, sodium sulfide. I think this was actually on one of the recitations. So in this instance, sodium is always +1. It's never anything else. And sulfide, which is not to be confused with sulfate or sulfite, those are polyatomic ions with oxygen in them. Sulfide, when it's at IDE, that means basically it's an element that's been turned into an ion. So it's a monatomic element, a monatomic ion, sorry. So if we need to balance these charges, we see I have 1 positive, 2 negatives. I'm going to need to double my positive ions in order to balance the whole thing out. And if you get confused about what to do, we basically do the old crisscross applesauce. But remember, we don't include the 1. If there's no number there, we assume that means 1. So we don't include the 1. So it's understood. It's like, yeah, I get it. You got 1. And you leave it out. All right. So sodium and bromine, what would be our formula for that one?
May I say?
Sure.
NaBr.
So 1 sodium and 1 bromide. That's right. So +1, -1. So we put them together, it's NaBr, which probably tastes a lot like sodium chloride. I've never tasted that particular salt. So what about sodium and oxygen? Who wants to take that one? I've kind of given away what the sodium charge is already. So what if we wanted sodium and oxygen? What would that be?
Na2O.
Na2O. And what do we call that? What would be the name of that?
Sodium oxide? No.
Sodium oxide. Yeah, that's it.
Mhm. Okay.
Just sodium oxide. Exactly. Okay, and lastly, we've got, oop, get my mouse here. Ooh, aluminum and chlorine. Who wants to take that one?
AlCl.
AlCl. Would that be the end of it? And what will we call that? Nice whisper. Yeah, what's the charge on aluminum?
Oh, it's a +3.
It is +3. So how many chloride ions would I need to balance
It's
that out?
supposed to be 3.
I'd need 3,
Sorry.
exactly. Oh, don't apologize. We're here to learn. That's what we're doing. So yes, so AlCl3, and what will we call that?
Aluminum chloride.
Yep, aluminum chloride. We don't need to put the 3 because as we said a little while ago, aluminum is always +3, always, always, always. It's never anything else. And so we don't have to point out that it's +3. We should know that already. Right, very good. So polyatomic ions, let's talk a little bit about it. You dealt with it on your recitation. I just want to really make this point that to treat polyatomic ions as discrete units, because they're discrete units. Like sulfate is a ion by itself. So if I needed 3 of them, I wouldn't write S3O12 because that is some other weird kind of combination of atoms. This is a very specific combination of atoms that has a net -2 charge. And so if we have 2 of them, we have 2 discrete units. They don't combine with each other. In fact, since they're both negatively charged, they wouldn't even come close to each other. They'd drive each other apart. So they're not going to come together. They would be driven apart from each other because they're both negatively charged. They would repel, and you would have positive charges in between them. So parentheses tell you that that's a group of atoms that behaves as a unit. It is a discrete unit that behaves as a charged item or a charged force. It's together as a group. It's always together as a group, and it has a particular charge. So here, calcium phosphate, and you can tell this is probably not a very soluble, not a particularly soluble salt, because it's got so much charge there. Calcium is a particularly soluble, and phosphate is a particularly soluble. You put those 2 together, it is not going to be soluble. So we need 3 calcium ions for +6, and we need 2 phosphate molecules for -6. And then this bracket indicates we have 2 whole discrete units of phosphate ion, both of which are -3, okay? All right. So let's do formulas for each of these. So the first one, magnesium nitride. What would be the charge of magnesium? And what is the charge of nitrogen when it's an ion?
Magnesium is Mg, right?
Mg. Mm-hmm. Oops. So magnesium is Mg, nitride would be N. So what group is magnesium in?
2.
It's in group 2. So what's its charge going to be?
+2.
It's always going to be +2. Now, how many valence electrons, what group is nitrogen in?
15.
So how many more electrons does it need to get to the happy place? To get to 8. Remember, everybody wants 8 in their outermost shell, with a few exceptions, really small
more.
elements. Needs 3 more. So what's this charge going to be?
-3.
Don't have to whisper, Raymond. Let them figure it out. So we'll just pretend we didn't hear that. So if it has 5 electrons and it needs 3 more, what's this charge going to be?
-3.
Yeah, -3 for nitride. So what is going to be the formula for magnesium nitride?
Mg3N2.
Okay, let's see. Mg3N2, excellent. Now, cadmium. Ooh, what a cad. Cadmium iodide. Look at your period. Hopefully you got your periodic table. Everyone should have their periodic table in front of them at all times, even when you're having lunch. So what group is cadmium in?
Cadmium.
CD, cadmium.
Is it in the transition metals?
It is not.
-40.
Group 40?
No, group 12.
So it would be a -6 charge.
No, it's always -2. Always +2. Sorry, +2. That one was a little tricky. +2. And so iodide is always -1. So CdI2 would be cadmium. Here's one that should be a little easier. Strontium fluoride. Strontium is a little more straightforward. What group is strontium in?
2.
2. So what's going to be the charge on strontium?
+2.
Mm-hmm. And since it's combined with fluoride ion, what's the charge on fluoride?
-1.
Yeah, it's always going to be -1. It's one of the ones that we're going to come back to over and over and over. It's one of the halogens, and they are always -1 because they're in group 17 or 7, if you want to look at it that way. They need one electron. They have 7, and they need 1 more. And we'll find out later that they're really good at getting that 1 electron, particularly fluorine. It steals that electron better than any other element. So it's going to be -1. So what's going to be my formula for strontium fluoride?
SRF2.
Touchdown. Yes, very good.
Excuse
And
me.
yes,
Cadmium is in transition metal, right?
yeah, sorry. Yeah, cadmium. Yeah, it should have had a 2 there.
Okay.
I apologize. Finally, cesium sulfide.
Cesium.
Where are you going to find cesium?
Did you spell it wrongly?
Sorry?
I mean, did you spell it wrongly?
Did I
In
just...
group 1.
Group 1. Yes, group 1. So what's going to be the charge on cesium?
1 plus 1.
+1. Right. And then sulfide, what's going to be the charge on sulfide? What group is sulfur in?
-2.
It's going to be -2, right? It's in group 6 or 16. So it needs 2 electrons. It's just below oxygen. And so if we know, basically because of the periodic table, and good old Mendeleev told us many years ago, that if oxygen is -2, if whatever elements are right below it, it's also going to be -2. That's what periodic means. And so it's in the same group. It's going to have the same charge. Nicholas, yes.
I'm still kind of confused on B. I'm looking at a periodic table and it might be wrong, but it's saying that cadmium is a transition metal, and I'm just wondering from what you said there has to be like a.
Yeah, there should have been a 2 there. I will. Yeah,
Oh, okay.
that slide had a problem that slipped past me. So
Oh, okay.
I will put that in there when I change it.
Okay, thank you.
Yeah, keep pointing that out because yeah, you made a really good suggestion about one of the labs yesterday that was very helpful. So yeah, we're always looking for fresh eyes to see these things, because when we look at them, it's like, oh yeah, cadmium is usually +2. Well, yeah, but you don't know that. And so it should have a 2 there. So I will make that change. Anyway, cesium sulfide. So we figured out cesium is +1, sulfide's -2. What's going to be my formula for cesium sulfide?
CS2S.
Let's see. Bingo. Yes. So cesium is really heavy. Cesium, if we think about when you throw sodium into water, it explodes. The bigger the atom gets, the easier it is to form that +1 ion. So you can imagine if you took a big hunk of cesium and threw that into water, kaboom, that's going to make a big explosion, because it desperately wants to lose that 1 electron to make a +1 charge. Sulfide is, yes, go ahead.
I have a question. Sorry.
No, never apologize.
I'm still trying to understand how you guys are getting the charges. I understand that the metals, it seems like they're getting a positive charge and the non-metals are getting a negative.
Yep.
How are you getting the -3 for A? How did nitrogen get a -3?
Excellent question. So actually, when we go back to the periodic table, we find that oxygen is in group 6 or 16. So oxygen means it has 6 electrons furthest away from it. That's what the group means. Basically, is how many electrons does it have in its outermost shell, furthest away from. I'll get to you in a sec, Nicholas. So how many electrons does it have furthest away from the nucleus? Because it's those electrons that are involved in forming bonds. And so with the metals, if you're in group, like for instance, sodium is in group 1, meaning it has 1 electron furthest away from the nucleus that's involved in bonding. Well, the easiest way for it to go back to having a full set of electrons is to lose that. And so when it loses that, it becomes +1. Because once it loses that 1 electron, the next shell below it is full. And all the elements want a full electron shell to be stable. Now, oxygen has 6 electrons in its outermost shell. And everyone wants to get to 8, because 8 is the group with all the noble gases in it. All the noble gases that are in group 8 or 18 have 8 electrons in their outermost shell, with the exception of helium, because it's so tiny. So everybody wants to get to 8. So the quickest way for the nonmetals to get to stability of a full shell is to add electrons. It'd be much more difficult for oxygen to lose those 6 electrons than it would be to just gain 2 more to get to 8. And when it gains those 2 electrons to get to 8, it now has more electrons than protons. It gained 2 additional negative charges. So oxygen is -2. But when we look at nitrogen, what group is nitrogen in?
5.
5, meaning it has 5 electrons furthest away from the nucleus. So in order for it to achieve stability, it can either lose 5 electrons and get a +5 charge, or it can gain 3 electrons and get a -3 charge. And it's simpler for nitrogen to gain 3 electrons than it is to lose 5. losing 5 electrons is difficult. And we'll get to why that is in a little while. But non-metals, sort of the thing to remember is non-metals on the right side of the periodic table gain electrons. They take electrons from metals. Metals lose electrons. So if you want to know what charge a non-metal is going to be, count and see how far away is it from the noble gas. Oxygen is 2 away, so it's going to have a -2 charge. Chlorine is 1 away. It's going to have a -1 charge. Nitrogen is 3 away. It's going to have a -3 charge. How far away are you from getting to a noble gas? That tells you what its charge is going to be. Okay?
Okay, thanks for clearing that up.
Oh, no problem. No problem. Half the class didn't know that either, and but you were the one brave enough to ask. So I'm glad you did, because it means that it wasn't explained well enough. And we haven't got to how the electrons are organized. Hopefully, which we're going to do in the next chapter. Hopefully, when we do that, it'll start to make a lot more sense. Okay. So molecular compounds. Oh, right, Nick, I didn't get to you. Sorry. What was your question?
That's fine. From looking at the periodic table, how do we know how many electrons would be needed to be lost or gained for transition metals?
You won't. Until we start looking at how the electrons are organized in their different orbits, you won't know that. That's what we're getting to in the next chapters, how the electrons are organized in different levels. And when we start looking at the different levels, we will learn that you can put some electrons here, you can put some electrons there, you can put some electrons there. And the different places where electrons go have different stabilities. And so some atoms, some ions will be formed by putting electrons in one place and forming a specific charge, and some ions will put the electrons in a slightly different place and have a different charge. But we're getting to that very, very question.
Okay, thank you.
Yeah, because transition metals are tricky. The group 1, there's a reason why we call the main elements, groups 1, 2, and then 3, 4, 5, 6, 7, 8. It's because it's relatively straightforward how they arrange their electrons. The transition metals arrange their electrons in a more confusing way. And so you need to think about them a little bit more. It's like a puzzle pieces. We can put those puzzle pieces together in different ways. They fit together differently. Yeah, good question. Because yeah, we're gonna get to that. Mm-hmm.
Okay, thank you.
So we talked about ionic compounds. Let's talk a little bit about molecular compounds. Molecular compounds don't have any charges in them at all, unless they're polyatomic ions, and that's a slightly different thing. But let's just talk about compounds for right now. So they are sharing electrons, as I've mentioned before. So instead of having the situation where if I have sodium and chloride, if they have a chemical bond, it's because sodium gave an electron to chlorine, and chlorine took an electron from sodium. And so that sodium is now positively charged, and chlorine becomes chloride and has a negative charge. In this particular situation, if I have something like carbon monoxide, there's no, or let's say carbon dioxide. That's carbon monoxide is kind of a tricky one. So this is what carbon dioxide would look like. There are every bond, every line here is a pair of shared electrons. So those are electrons that aren't really owned, let's say, by any particular atom. They are shared in between. So oxygen has 6 electrons. It's in group 6. Carbon has 4 electrons because it's in group 4. And this oxygen also has 6 electrons. So what's happening is that they're sharing a pair of electrons here and a pair of electrons there. So now oxygen can say it has 2 of those shared electrons. So now it has 8 and it's happy. So this oxygen is in the same situation. It's happy. And the carbon is sharing 1, 2, 3, 4 pairs of electrons. And it can say half of them belong to it. And now it also has 8 electrons. So everybody's happy because everyone's sharing. We'll learn that they're not sharing equally, but they're sharing electrons. So there's no charge. And because there's no charge, these generally, like as we saw with sodium chloride, it takes a lot of energy to break this bond, to pull these things apart. Now, with covalent compounds or molecular compounds, you don't break these things apart by just heating them. They're chemical bonds that you can't break simply by heating it up. So they don't break. And so they often exist as gases or liquids with low boiling points, or solids with low melting points, because they don't break. They just sort of they act as a unit, and we'll say a non-polar unit. So you remember when we did the lab looking at polar things and non-polar things, or hydrophilic and hydrophobic things. Generally, molecular compounds are more hydrophobic than ionic compounds. They're charged. They're very hydrophilic. They dissolve in water. A lot of molecular compounds don't dissolve in water. Like carbon dioxide will dissolve in water, but not very much of it. And if you warm water, like you have soda, which is just water with carbon dioxide in it. If you warm that up, or you would know that if you leave soda out on the counter for any period of time, the carbon dioxide comes out of it. So it's not particularly super soluble. So they have different properties than ionic compounds do. So yes, go ahead.
Why would the molecule carbon dioxide become ionic when it dissolves in water?
It doesn't.
I mean, hydrogen company.
No, it doesn't dissolve it doesn't become ionic. What happens when it dissolves in water? Yeah, it forms carbonic acid.
Mm-hmm.
Yeah, basically it's because
Yeah.
that's a chemical reaction where the oxygen attaches to the oxygen attaches to the CO. Oh, let me go back. Attaches to the CO2 plus water. That gives us carbonic acid. So it adds another oxygen to the CO2 and turns it into an ion. But that's a chemical reaction.
Okay.
Yeah, this isn't an ion. It becomes an ion through a chemical reaction.
Does it break the bond?
Yes. No,
Okay.
well, it makes a new bond. The
Okay.
CO2 stays intact. We just add another oxygen to it.
Okay.
Yeah, and it's one of those reactions that doesn't go to completion. This is an equilibrium back and so this reaction goes in both directions. And in fact, it's this reaction that keeps the pH of your blood approximately 7. Something to know. Anyway, so nomenclature. We sort of done a little bit of this already too, without really knowing what the hell we were talking about. So compounds, we pretty much know how to name ionic compounds, but with covalent compounds, we need to to say exactly how many atoms are in a covalent compound, because in an ionic compound we pretty much know, because things are charged. They're going to follow a distinct pattern. This many atoms is going to have this charge. This many atoms is going to have this charge. So I know exactly how they're going to fit together. when you have a covalent compound, like for instance, we have carbon monoxide and we also have carbon dioxide. So if I say I have a compound with carbon and oxygen in it, it could be a lot of different things. And so we need to say, that's why we use the term carbon monoxide to say that there's one oxygen, and carbon dioxide to say that there's two. We have to, because there's different ways. Okay, there's different ways that nonmetals can share electrons. They can share one. They can share one pair of electrons and form a single bond. So for instance, carbon can share one pair of electrons with another carbon and form what's called a single bond. Carbon can also share two pairs of electrons, for a total of 4 electrons with another carbon and form a double bond. Carbon can also share 3 pairs of electrons with another carbon for a total of 6 electrons and form a triple bond. And so ions don't do this. They have a charge and they come together in a reproducible way, whereas nonmetals share electrons in all kinds of different ways, and so they can have different kinds of bonds. And so we need to say exactly how many atoms are there. So when you name ionic compounds, this is something that we've sort of been doing that I sort of didn't mention though, but the metal, the cation is always named first. So sodium sulfide, potassium bromide, the metal comes first. And then the monoatomic anion, the negatively charged one, we just give it the ide name. So if it's sulfur, sulfide, oxygen, oxide, iodine, iodide. Okay, so we sort of know that one. So calcium and fluorine, we pretty much know that in this instance, calcium is going to be +2. Fluoride is going to be -1. And so calcium fluoride. And aluminum, we've been dealing with aluminum all morning. We know aluminum is going to be +3. And oxide going to be -2. We do our crisscross applesauce. Al2O3, aluminum oxide. And so we don't need to say in the compound name how many aluminums and how many oxygens. It's because reproducibly, aluminum is always going to be +3. Oxygen's always going to be -2. So we don't have to say it's going to be Al2O3 because, well, it's always going to be that. But when you have nonmetals that can form bonds in different ways, like I showed with carbon monoxide, carbon dioxide, nitrogen can form a whole bunch of different compounds with oxygen, depending on how many electrons they share. So if I said nitrogen oxide, you don't know what I mean. That could be a lot of different things. But, mononitrogen dioxide or dinitrogen trioxide, that says exactly what the compound is. And we need to do that for molecular compounds. So transition metals, again, we sort of been through this. You need to say what the charge is going to be, because there's only a couple of transition metals that have the same charge all the time. You remember that zinc, oops, what the hell happened there? Zinc is always going to be +2. Silver is always going to be +1. Other than that, it's a free-for-all. And like chromium, for instance, can have a lot of different charges, anywhere from like +1 to +7. And it's usually either +3 or +6, but it can be a lot of different charges. And so you have to say, if you have chromium chloride, that's a lot of different potential compounds. So you have to say, is it +3? Is it +6? Is it +7? Is it +5? You have to tell me, because if you say, go get some, if I'm doing a reaction and I need some chromium 6 chloride, if I need this, and I need very specifically, I need that compound, and you bring me something different, if you bring me chromium 3 chloride, that's not going to work in the reaction I'm doing. So it's you need to be extremely specific what particular compound it is.
Do you need to use Roman numerals for silver and zinc?
No. Good question. You do not need to use them because silver is always +1. And so, and zinc is always +2. So you don't need to put silver 1 because that's redundant information. It's already known. Just putting silver chloride is always AgCl. It's never anything else. Yeah, good question. So you don't have to do that. So transition group metals can have more than one charge. We know this. So iron oxide means different things. So in this particular example, this iron has a +3 charge. So we'd have to say iron brackets 3 oxide. If it was iron 2 oxide, what would be the formula for iron 2 oxide?
FeO.
Just FeO, much simpler. And so you could see that like the molar mass of iron 2 oxide is much less than iron 3 oxide. Iron 3 oxide weighs more than twice as much. And so big difference can be made just by, one electron difference between iron 2 and iron 3. All right, so I think we've done these enough. I'm just going to keep going because I desperately want to get through chapter 2 today. So molecular compounds, different set of rules, because as I've been mentioning, the variation of sharing electrons. The electrons are not shared the same all the time. So there's an example here of carbon and oxygen. Carbon monoxide has a triple bond. There's 6 shared electrons between the carbon and the oxygen. And as I showed you with carbon dioxide, there's 2 double bonds. So the carbon in the middle is sharing 4 electrons on one side, 4 electrons on the other side for a pair of double bonds. And they can also form single bonds, which is just a single pair of shared electrons. So if I give the name of a compound that has these nonmetals that can share electrons in different ways, you have to say exactly how many atoms are in a particular molecule, because carbon oxide can be a lot of different things. Nitrogen oxide can be a lot of different things. So you have to say specifically what it is. Whoops, let me go back. So how do you name those? So this is a little bit tricky because, as I mentioned with the ionic compounds, the metal always comes first. Well, we don't have a metal now. What the hell do we do? Well, the more metallic element, the one further to the left, or the one further down on the periodic table, we name that one first. So when we have carbon and oxygen, carbon is to the left of oxygen, so it comes first. If we have nitrogen and oxygen, nitrogen's to the left of oxygen, it's named first. If we have oxygen and fluorine, oxygen is to the left of fluorine, so oxygen would come first in that particular example. So we have whatever one is to the left or further down comes first. We name that one first and we just give it the name. And then second, we give it the more non-metallic element, the one closer to the right, the one closer to the noble gases. We just give it the normal name with "ide" at the end, just like we would with an ionic compound. But the difference, is we use these Greek prefixes to say how many atoms. Yes, Nick.
What's causing something to be more metallic? Like, besides us just saying just do it in that order, what is the actual like reasoning behind it? Is it like something has more electrons than others, that cause it to be more metallic?
Yes, actually. We'll learn as we look more closely at the periodic table. The further to the left you go, those elements can't hold on to its electrons as closely. And as we get further to the right, closer to the nonmetals, closer to the noble gases, as we get further and further to the right into group 5, group 6, group 7, those elements hold on to their electrons and in fact pull away electrons from other elements. So what we say is that more metallic E, the more metallic nature means that you can lose electrons. You don't hold on to electrons as tightly.
Electronegativity?
Yes, electronegativity. And as you move to the right, they pull on electrons more. So if you pull on electrons more, you're considered more non-metallic. And if you can't pull electrons as tightly, you're considered more metallic. So as you go to the left, you're more metallic. And if you go to the right, you're more non-metallic.
Okay.
And the same is true with bigger. The bigger an element is, the further and further away those electrons get from the nucleus. And the further they get from the nucleus, the less of a pull the nucleus has on them. And so they become more metallic in nature.
Okay.
Okay? Yeah, we're gonna get to that very thing. But that's an excellent question. It is full of good questions. Anyway, so we need to remember some Greek prefixes. But even if you don't remember them, I got them in the table there. But you're probably familiar with a lot of these. Mono, di, tri, you're probably really familiar with those because we use those all the time. The ones that we don't see quite as often are like 4 to 10. So tetra, penta, hexa, and then really we don't use these ones at the bottom very often, but hepta, octa, nona, and deca. But generally, it's the first 6 that we're going to use more. We use those pretty frequently for naming covalent compounds with a lot of with those specific numbers of atoms in them. So we usually omit the mono if it's the first element. So for instance, carbon monoxide, I don't say monocarbon monoxide because you usually just assume that if it's the first element, there's one, unless there isn't. So if I had N2O3, for instance, I would say dinitrogen trioxide. If I just said nitrogen trioxide, it would be assumed that there's just one nitrogen there and there's 3 oxygens, okay? But if it's the second one, basically always say mono if it's the second element in there. If it's the first one, you generally don't have to use it. And then when the 2 vowels are adjacent, just for naming, if there's 2 of them together, like an A and an O together, or 2 O's together, we generally just drop them and just use one. So instead of monooxide, we just use monoxide, okay? And if we have tetra oxide, we usually just say tetroxide. So one thing there. All right, so what would be the formula for carbon disulfide? I'll let you answer this one. Carbon disulfide, what would it be?
CS2.
CS2, yeah. And it has a lot of the same properties as CO2. It's also a gas. So PCl 5. What will we call PCl5? What would be the name of it?
Phosphorus pentachloride.
There you go, phosphorus pentachloride. That's a fun chemical because actually it explodes when you touch it. If you can paint something with phosphorus pentachloride, let it dry, and then if you touch it with the tip of a pencil, it goes boom. So that's fun to play with. So what would be? I have a compound with 2 nitrogens and 4 oxygens. What would be the name of it? First, give me the formula of it. Which element would come first?
N2O4.
Right. Nitrogen is in group 5, oxygen group 6, so nitrogen comes first. So it would be N2O4. What would we call it?
Dinitrogen tetraoxide.
Well, we wouldn't say tetraoxide. We would shorten it. Tetroxide. Yeah, just tetroxide. You'd be okay with tetraoxide, but generally, yeah, chemists are always in a hurry. We need to shorten things down. Yeah, so we would say tetroxide. So CS2, phosphorus pentachloride, yeah, or tetroxide. So you'd be fine either way. Not to worry too much about that. So incorrect name. So if you saw these, there's something wrong with them. Can you tell me what it is? So SF4, monosulfur pentafluoride. What's wrong with that?
We don't need mono.
Don't need mono for one thing. Is there anything else?
Penta.
Mm-hmm. What does penta mean?
5.
5.
5.
Right. So 2 problems with that one. What about the second one? Dichlorine heptoxide is Cl2O6.
Hept. Did we say heptoxide dichloride? Heptoxygen.
It's supposed to be
6.
Hexa. Yeah, that's right. That's one problem. Hexa. Hepta means 7, and there's only 6 oxygen, so that would be hexoxide.
Also, Professor, what will be the charge of these compounds?
No charge. Remember, these are covalent compounds. There's no charge on them.
Do we write oxygen first, then chlorine?
That one's a little trickier because chlorine is below oxygen, but also to the. So we'll see about that one. What about the last one? N2O3, dinitrotrioxide. That looks fine. What's wrong with that?
Dinitrogen.
Right. Nitro means it's an ion. That's a different compound. Nitrogen. It is nitrogen trioxide. So dinitrogen trioxide. So sulfur tetrafluoride. Now you mentioned before whether chlorine should be first or second. Since chlorine is lower on the periodic table, and that's, like I said, that part is a little tricky. Chlorine is lower on the periodic table, so it's considered more metallic. Now, if it was oxygen and fluorine, they're in the same period. They're in the same row. So that is cut and dry. Fluorine is further to the right. Oxygen is to the left. So oxygen would come first and fluorine would come second. But when something's bigger, then we say it's more metallic. Okay. And then the last one, yeah, dinitrogen. It's not nitro, it's nitrogen. You have to say the name of the atom, trioxide. Excellent work. So acids. So We haven't really talked much about acids and bases. We talked about them a little bit. Acids are substances that when you dissolve them in water, they release hydrogen ions. And we also call those hydronium ions because they will mix with water and form this ion. And so they get that sharp taste to them, that acidic, sharp taste. And the pH goes down when you dissolve an acid in water. And the molar concentration of hydrogen ions or protons, that's what they are, goes up. And so we name these particular things with a particular name when they're dissolved in water. And this part is key because HF by itself, if I just say HF, that's hydrogen fluoride. That is a gas. But when I dissolve HF in water and I give it aqueous, and again, this is one of the reasons why the state of matter is so important, because there's a big difference between HF, the gas, and HF, the acid. One is dissolved in water and forms ions, and the other one isn't. It's a gas that you do not want to breathe in, believe me. So when you're naming, these are called binary acids. Binary just means there's one atom, there's two atoms. One of them is hydrogen. One of them has to be hydrogen because when you dissolve it in water, it's able to break that bond and release H+. Now, a strong acid means that it breaks completely and you get nothing but H+ and, in this case, Cl-. It breaks completely. That's a strong acid. Now, once you, that is true for HCl, HBr, H2SO4, and nitric acid, sulfuric acid. There's basically like about 5 strong acids. Everybody else not break completely. Interestingly, one of them is HF, does not break completely. So when you're naming these things, you change hydrogen, so it's no longer hydrogen fluoride. You change that to hydro.
You said HF doesn't break completely?
Mm-hmm. It doesn't ionize completely. Yep. We'll explain why a little bit later. Then the non-metallic element, we just put ic at the end, basically saying that it forms an ion when you dissolve it in water. So hydrofluoric acid. Hydro meaning it has a hydrogen on it. Ic meaning part of it, if not all of it, ionizes when you dissolve it in water. So hydrochloric acid, probably no doubt familiar with that, just means you have a hydrogen and a chlorine. It's a gas when it's just HCl, but when you dissolve it in water, it becomes hydrochloric acid. HBr, hydro again, and bro, mic this time. And sulfide becomes hydrosulfuric acid, which is different from sulfuric acid. And we'll explain that in a bit. So that's a binary acid. You always have hydro when you have a single hydrogen or just, hydrogen and another single element. Now, there's a different set of rules when you have these polyatomic ions that have oxygen in them, and there's a ton of those: phosphate, sulfate, sulfite, chlorite. I mean, there's a whole bunch of chlorate. There's a bunch of these different things. Now, in these particular instances, we take the hydrogen out. We just assume, because we're going to say it's acid, so we assume there's a hydrogen there. And we start with the root name of whatever polyatomic ion it is. Now, if it's something like phosphate, we replace the ATE with ic. And so we would have phosphoric acid. And phosphoric acid is actually the acid that's in Coca-Cola to give it that fizzy taste, that the slightly acidic flavor. That's phosphoric acid. So that one's not particularly dangerous. If you have ite, like chlorite, you would say chlorous acid. Then you put acid at the end to tell us it's an acid. So remember, you do not have to memorize all these names. It is in the tables for you. I just want to show you how it works. So we have bromide there. That would be hydrobromic acid. Now this is a polyatomic ion. Remember one of the ions you had in your last recitation was IO4. That was periodate ion. This is iodate ion. So what will we call that acid? If it was iodate ion, what would we call it?
Iodic.
Iodic acid. Yep. Anyone know what this ion is? This is a very famous one.
Toxic.
Cyanide?
That's cyanide. Very good. Yeah, that's cyanide. So if it's cyanide, what will we call the acid? HCN.
Hydrocyanic.
We don't use the hydro.
Did you
yes,
say cyanide?
Sorry, yes, we do use the hydro because it doesn't have oxygen. Yeah, hydrocyanic acid, which is something, yeah, you don't want to have that either. That will also kill you. So we pretty much know that that's sulfate, right? That's a super common polyatomic ion. There's a ton of different sulfate ions, sulfate compounds out there. So if we add H2 to it, since this is -2, we need 2 hydrogens to balance it out. So what would we call this acid when we dissolve it in water? So we go from sulfate to
Sulfic acid.
what will we call it?
Sulfic.
Sulfuric. Yeah.
Sulfuric.
So we need to have the F in there to sort of let us sulfuric acid.
Excuse me.
Yeah.
Why we need acid there when we name it? Why we don't just assume it from the name?
Because basically we're talking about it when it's in solution. When these things are in aqueous solution, they are acids, and so we basically have to say that they're acids, because some compounds with hydrogen in them are not acids. So we have to say that in these particular instances they are. You need to identify them as acids.
Okay.
Yeah. So the last one, NO2 to NO3 is nitrate. So NO2 is nitrite. So what will we call nitrite with one H? That when we dissolve this in water, what would we call that one?
Nitrous.
Nitrous. Very good. Nitrous acid, which is different from nitric acid. So what are the rules for doing these? Now, you take the ion name and you add an ic to it if it has an 8. So if I have an acetate or nitrate or perchlorate, I change that to ic. If it has an ite at the end, ITE, I change it to us. Now the difference is 8 means it has one more oxygen in it. And I think we talked about that last class. The most number of oxygens you can have, we would say per. That is the maximum per and 8. It's the maximum number of oxygens you can have in a polyatomic ion. Like if you can have 4 different ones. If you can't have 4 different ones, the next one down would be just 8 by itself. And then the next one down from that would be ite. And then down from that would be, I can remember, hypo with ite. That's only if there's 4 different ions available. If there's only 2, you use 8 and ite. Ite being the fewer number of oxygens, 8 being more oxygens. So that's the only difference. Now again, don't have to memorize this. It's in the tables, okay? But we're dealing, a lot of these you're going to see over and over again. You're going, like acetic acid, that's vinegar. You're going to see that in a lot of chemistry questions. Nitric acid is one of the strong acids. So that dissociates completely, that ionizes completely in water. So that is going to be used a lot. Sulfuric acid separates completely in water. So that is one of the strong acids. And then phosphate, as I mentioned, that we're going to see phosphoric acid occasionally. So those are the sort of the main ones to think about. Carbonate or carbonic acid I mentioned before, that comes when you dissolve CO2 in water. And so that's a fairly important biological acid. Because I said, that basically keeps the pH relatively neutral in your blood. So when you're breathing out CO2 or breathing in CO2, some of that dissolves in your blood and forms this and keeps the pH of your blood around above 7. Yes.
All the oxygenide acids forming from a non-metal oxide and react with water.
I didn't get that. Sorry.
Like carbonic acid is forming from carbon dioxide with water. Are all of the oxy acid forming the same way?
No. It's just that this particular one does. Although there's different ways that, like, carbonate can form in a lot of different ways.
Okay.
Yeah. So, man, we were out of time. I went long, and we still haven't got to chapter 3. So definitely we will get to chapter 3 on Thursday, because now we're done finally with chapter 2. So anyone have any questions before we go? I know we had the introduction for the Learning Center first, so we missed some time. But at least now we're done with chapter 2. And so chapter 3 in your book, I believe it's chapter 6. So we're starting quantum theory and atomic structure, the structure of the electrons outside of the atom. And this basically, this is one of my favorite chapters because it basically explains all of chemistry. So if you can get that, the rest of it is pretty easy stuff from there. So any questions before we go?
When do we submit the recitation for?
I think it's due Thursday.
I don't think the submit button is ready.
Okay.
Okay.
I'll put it in there.
Okay. And why are the acids liquids and gases, but the bases and the salts are solids? Solids.
bases or solids?
Like like calcium hydroxide, magnesium hydroxide.
Yeah,
They are solid.
because they're all ionic compounds. All
But
the
acids,
oxides are ionic, so they're
but
solid.
acids are gases.
Mostly, not all.
Some are liquids.
Yeah, phosphoric acid is a liquid.
So acids are ionic.
Not when they're not dissolved in water. They're not.
Oh, okay.
Yeah.
I have a question regarding last lab.
Sure.
So the new question that you, I guess you reworded it. If we already submitted the lab, do you want us to resubmit the lab with that new question or new reworded question?
If you didn't think you answered the question properly the first time because the question itself was kind of vague and assumed you knew things that you had no point, you had no business knowing. So yeah, if you want to resubmit it without a penalty, yeah, please go ahead and do that. Yeah.
Did you say the last lab was the sample was collected from 1 kilogram of soil?
That's right.
But would would the percentage of mass be the same though from the sample?
No, because if you assume that the sample was just the liquid, was just the extract, that's like 100. That would be 100 milliliters.
Oh,
okay. So
okay.
you'd assume that it's going to be around 100 grams.
So the 100. So the all of the extract is 100 millimeters, right?
Yes.
Okay.
For sample 1 and 2, yeah, they're 100 milliliters of the extract. Yeah, and then the known sample was 100 as well.
Okay. And how do we fill in the second column, the 1.0 m AgNO3? Do we all put 100 mils or put the how many it reacts?
You put how much you put in there. That's the silver. How much silver did you use?
Did you say we should put excess of silver nitrate? We should put
you have
excess
to.
of it?
Yeah, you have to.
So
you keep adding it until the amount of precipitate no longer increases.
I mean, do we put the amount we put or just?
Yeah.
Okay.
That's the point of having the data table. You put in how much you actually added.
Okay.
Yep. All right. Any other questions before we go? So I posted lab number 4. So that's the one we'll be doing this afternoon. It's a pretty I don't know if it's straightforward. It's pretty short. So we probably won't be meeting for a long time, but it'll be fun to do. Again, on stoichiometry. I want to focus on doing as much of that as possible before moving on. Yes, Nicholas.
I had a question kind of relating to this. Do you want me to wait till lab?
No, go ahead. We're here.
So I'm planning on studying biology, and I would like to work with like primates and stuff.
Mm-hmm.
So this last lab, how would do I have to study biochem to be able to study this kind of problems of the water supply and stuff like that, or is that?
Yeah, I mean, it definitely wouldn't hurt. I mean, if you're thinking about going into biology, then yeah, I think you should definitely take a biochemistry class.
But it doesn't have to be my bachelor's is based on, or my master's is based on biochem. Because what I was thinking is going the route of environmental science for my bachelor's and then master's for biology. But this kind of experiment is kind of what I want to concentrate on, is kind of
oh yeah. Hell, there's you can get a bachelor's degree in environmental chemistry.
Oh, okay.
Yeah. So, yeah, but definitely have a biochem class in there because you need to understand why these toxins are toxic.
Yeah.
And so, without a good understanding of biological chemistry, you're not going to understand why that is. And so that's kind of important.
Okay. Thank you.
Like cyanide
Yeah.
is poisonous for a different reason than arsenic is poisonous. Well, how come? With a background in biochemistry, you get to know that.
Excuse me.
Yes.
Why we named the cyanide like the monoatomic ion? The cyanide. Why we name it like cyanide instead of cyanate?
Because if you have 8 in it, that means there's oxygen present. There is a cyanate ion, which is different from cyanide ion. And that's a shorthand anyway. I mean, it really should be called carbon nitride, right? But it isn't called that because that is a compound. And so it's sort of given the shorthand cyanide to let you know that it has a charge.
Okay.
Yeah, cyanate. If you have an 8 or a ick or an us or anything like that, it means there's oxygen present. And with CN, there isn't any oxygen. Yeah, Nick.
Sorry, one more question about the experiment. So would you test vegetation this way to see if like large primates or like gorillas, their vegetation for some reason is dying? Is this the same kind of experiment you would use to kind of figure out if there's...
Definitely, yeah. You would take the leaves, you take whatever they were eating, and you would extract them with different compounds. You'd extract it with something aqueous, like probably like you'd extract with a water that's with a low pH, like something acidic, that would extract most of the basic compounds, and then you would take some and you would extract it with a base that would extract the acidic compounds, and then you would extract it with something like ethanol or methanol or something organic to extract specifically the nonpolar compounds, and then you would analyze them separately. So one would have the one extracted with acid would have a higher concentration of basic compounds. The one extracted with a base would have a higher concentration of acidic compounds, and the one extracted with an organic acid would have a higher, or organic solvent would have a higher concentration of organics. And then you would test them, the 3 of them separately, and look for specific things. Yeah.
Okay, thank you.
That's exactly how that would work. Mm-hmm.
Thank you.
Okay, man.